Okay, so
A speaker.
will talk, which is going to talk about recurrence dynamics from data.
So, very good afternoon once again to all of you. This, as Neelima wanted me to do a little bit tutorial type, this is going to be like that. Most of my main results I have already given on that day in the previous lecture. Now I will take you through the detailed steps and explain to you at each stage how are we checking, what are the things to be taken care of when you actually deal with data and these type of things. And previous speaker, you were asking the previous speaker about the reference for Lyapunov exponent calculation. This is the most standard paper, even though it's an old one, by Wolf. It's called the Wolf algorithm. That can be used for equations as well as data. Starting from equations, you can get all the Lyapunov exponents, and starting from time series also. And for anything in time series, there is a good package called the TCN. And they have a paper also explaining how to download it, how to install it, how to do it, etc. So TCN stands for time series analysis, first two letters. So it's easy to find it out. And then for all these recurrence related things, the TCN will not contain recurrence related things. It's the early days when they calculate other fractal measures from time series, etc. The recent one that I'm going to talk about is given in this package. That's called the Pi Unicorn package. Can you read it? PYUNICORN, Pi Unicorn. It is in the Potsdam site. As you can see, that site is also given here. This is for recurrence measures. And anybody who is interested and would like to do more, send me an email. One of my students have developed a package which is also available online. It's called FRAPPY, F-R-A-P-P-Y. That also can be done. So let us see. So we were basically saying that you can reconstruct the dynamics from data. So in that sense, this is slightly different from generating networks that you have so far heard by looking at correlation between time series, etc. So for each individual time series, we are actually looking at the dynamics underlying that, the argument being that there must be number of dynamical processes, internal and external influences, because of which the data comes with some structure. So basically, you are again looking at the structure in the data, but using a dynamical systems approach where we find out the dynamics underlying that, look at the dynamical features, and then say something about the data. So this will be useful for looking for the recurrences. That is one way of characterizing the dynamics. But I will mention to you one or two other ways also. Then from that you can calculate it, and climate data I have already given all the results in detail. So I will show you, just to inspire you, I'll show you some other interesting data sets from astrophysical data, binary star data, and physiological data like ECG, etc. And then transitions can happen in finance data. For example, the global financial crisis, GFC, into 2008. Can we say what happened to the dynamics underlying financial market just before that? So in a way, people are now looking for some early warning signal, which will tell you that some transition is going to happen. So if you can say that, then it is better to know that, and some measures can be taken, protective measures or mitigating measures, whatever can be done, that will be good. So I'm not going into very much detail there, but I can tell you a few things. Okay. So just to tell you a few more data sets, climate data sets we have already seen. This is an astrophysical data set from a variable star. So there are large number of pulsating variables, or the ones called irregular variables. The intensity of those stars vary in a very irregular way. The reason being that there are nonlinear processes involved in producing the intensity, and therefore the pulsations for a star like Cepheid, the pulsations are exactly regular and periodic. But there are large number of variable stars where they are not exactly periodic. As you can see, this gives the intensity flux from one particular variable star. And this, as I said, is the EEG data. All of you know that what is EEG data. This is for a healthy person. This is for an epileptic patient during seizure-free interval, and this is during seizure. So there is a lot of information required, and there is some relevance in studying, comparing such data sets. Not only looking at one data set, but from a normal person during seizure, during seizure-free interval, can you look at what happens to the underlying dynamics, what changes happen, because of which seizure happens, and then can we do something about it, at least characterize it? That will be a challenge. So that is why I'm just showing that also. And all these climate data we have seen earlier, temperature data, relative humidity data, etc. Now I am showing you two data sets, this one and this one. So visually, if you look at it, do you think what sort of data, what sort of a system generates this data? Can we say there is a deterministic dynamical system that generates this data just by looking at that? This is just to tell you that there is some reason for doing some more analysis of data rather than visually looking at data. Because if you look at this data, very difficult for us to estimate the differences between them. But now I am going to tell you that this data is produced by a trajectory of this type. Anybody has seen this trajectory? Which system produces this? Anybody done a course in nonlinear dynamics? It's a Henon map. So it's a nonlinear system and it produces this type of a data when it is in the chaotic region. On the other hand, this data is produced by totally white noise, stochastic system. So even by looking at this, if you don't recreate the dynamics, we won't be able to say what is the difference between them. One is deterministic, one is stochastic. So that is the reason. Now, pre-processing we have already discussed earlier, but let me take you through these different steps once again. We said most of the cases we would like to, because especially when you are comparing data sets having different ranges. For example, Lorentz system, goes all the way from minus 40 to plus 40. Rosler system goes only from minus 20 to 20. And some of the maps only are within 0 to 1. So suppose you want to analyze all of them, it's always good to have them rescale to one particular interval, which we usually take to be 0, 1. So the process is very simple. We take every point in the data is xi, let us say. We take xi minus xmin by xmax minus xmin. That is your new data set now. So it means the minimum value will now give 0 and the maximum value will give 1. That's all we want. So if you do it for every point in your data, you are going to get a data set which is only confined within 0 to 1. This is one way of doing it. There is another process called taking uniform deviate that is little more detailed, where you will adjust its distribution also as a uniform distribution. This is also one way of pre-processing, especially useful when you want to compare data sets. And we talked about binning. There was some question in the previous lecture about binning. Why do you want to bin? So binning means, suppose we decide on a bin size. Suppose I say I have a large number of data sets, 50,000 points. I choose a bin size of 10. So the 10 values within that 10 we will replace by its average and put it at the middle of that bin. So the number of data points available may decrease, but in many cases that is okay if you have enough data. Still, two or more advantages for binning. One is small fluctuations or noises will go away. Because if the actual values, sometimes little bit above plus epsilon, sometimes minus epsilon. So when you average over them, that will disappear. So little bit of smoothing is possible by doing binning. The third advantage is sometimes some gaps occur in the data. Because especially observational data, even though we say that all the data are sequenced in time, the sequences need not be equal. So what happens is you have data at time 1, 2, 3, 4 is missing, then you have only 5, 6, 7. So sometimes small gaps like that, they will not affect. In many cases, people just ignore them and just put them together so that the time information is lost. In many analyses, even that is enough. For example, the rainfall data analysis we heard here, we know that rain is not happening throughout the year. It happens only during the seasons. So if you take the rainfall data over so many years, what do you do with those big gaps when the rainfall is 0? Either you put them all as 0 or most of the cases just merge them. So after the last rainfall, the next season, first rainfall, they add to that. That's also done. So instead of that, here we make small gaps in the data. We can average over a bin, and the bin size you can decide depending upon the data gaps that you have and depending upon whether you can afford to do it, provided you have a large data set. If you have only 1,000 points and you bin it by some 10 bin of width 10, then your number is going to decrease. That may not be enough for any statistical analysis. So in such cases, you don't do it, but otherwise you can do it. And detrending is very important because there may be some inherent trends in the data. It's okay that trend is coming from the system, but the trend can mask some of the relevant quantities we are looking for. So we have to detrend. So that means removing the trend from the given data. It's usually a change in the mean over time. So If the data, instead of going like this flat, it goes like this. So that means there is a linear trend in the data. So that information we know, and we don't want it also for later calculation. So we would like to detrend. And some cases, the trend need not be linear. So this may not be desirable because they can mask other relevant information, and the trend can be linear, quadratic, or polynomial. So what we do is we fit a polynomial to the data, and then that fit is subtracted from the data. So then what remains will be your data without the trend. But sometimes the trend can be periodic also, especially for seasonal effects or climate data. We have a very strong annual periodicity and seasonal periodicities. So there, what you do is you take the Fourier transform and look at the major peaks there and use them to filter that strong peaks. Then you get a data which is filtered, which is detrended for all periodicities. So let us see how this is done. One case I am showing. So here, this is actually stock market data. The original data is this blue curve. And what we do is we fit a polynomial to this by the least square fit. We discussed in an earlier lecture here. Suppose y is equal to this. This is the data. We consider a polynomial of degree n. So which degree to choose again decides. Most often finalized by trial and error, so that we don't want to lose the dynamical changes in the data which we want to keep. So if you go for very high degree, they may go away. So we fix this degree, check it, and then the polynomial is subtracted from the data. So you look at this, all the interesting dynamical variations are retained. Nothing is lost. Only this trend is lost. It was going like this, and that is now lost, and that is now removed, and you are getting the detrended data, which contains all these minor fluctuations, minor variations, which comes from the dynamics. Now, periodic trends. Suppose there are periodic trends. As I said, you go to the Fourier transform using FFT algorithm, look at the prominent peaks and generate a multi-periodic fit using that, like this. And then subtract that from the original data and use only the residual data. This is how to remove the periodic trends. That's also done. So how I did pre-processing for the climate data, I showed you earlier, just to remind you. For the case of climate data that I used, I did only 2 points per day, beamed it like that. Then removed the highest peak coming from annual periodicity, and then used a moving mean with a window size of 30 to remove small fluctuations and seasonal trends, and then rescaled to 0 to 1. So once again, just to show you, this is the climate temperature data from Bangalore. This was the original data. This is after removing all the detrending or completing the pre-processing. So 0 to 1 now. Similarly, this is relative humidity from Pondicherry. This is the original one. After doing this processing, this is the data that you get. So that is the initial part where you want to do the pre-processing. Now, we already talked about embedding the data into a higher dimensional dynamical system. See, I will show you with some examples, but what I would like to say is, if there is a dynamical system which produces this data, there can be a large number of variables which together produce this, because these variables means some quantities which change over time, and therefore these quantities are connected because of interaction among some dynamical processes, because of which even one variable may contain information about the changes that happens to the other variables also. Therefore, even with one variable data, you should be able to reproduce the dynamics in that higher dimensional space, which involves all the other variables also. So let us take a very simple example, harmonic oscillator. We know that we usually write it as a second order equation, x double dot plus omega x equal to 0. Let us say simple undamped, unforced harmonic oscillator. Now, when we look at it as a dynamical system, we write it as a two-dimensional equation. We define x1 dot is equal to x2 and x2 dot is equal to minus omega x. So, even if you take only x1 values, it contains the information about how x2 values are changing. This is because all these are coupled, and coupling comes from the underlying dynamical processes which involves interaction among them. So that is the basic principle how to understand why a scalar time series can reproduce the dynamics in a higher dimensional phase space. Now, how do we do it? This we have shown the other day that we will just read off these values sequentially with a delay of tau. So this is the first component, second component, mth component. When you want to put it on a m-dimensional space. Tau is the delay time. So as we said, this tau and m are to be estimated separately for each data set, because that involves the nature of the changes that happen, the dimensionality of the system, etc. So one thing we said is, if the delay is very small, what happens? Because this tau, t and t plus tau, suppose we take tau equal to 1. So then what happens is every sequence point we are considering. So if that is the case, these values may be highly correlated, because of which the reconstructed dynamics may lie along the diagonal. So this is what happens if the delay chosen is very small. But then we say the dynamics is not properly unfolded in the space. So what we have to do is we have to go on increasing this delay until you find that it is properly resolved and you get the trajectories, proper trajectories. This, this is the trajectory of which system? Rosler system. Now, if delay is very large, what will happen? Again, it becomes totally uncorrelated. So it will look like a totally noisy behavior or stochastic behavior. So we have to strike a balance somewhere in between. I am coming to that. There are processes for doing it, but I am telling you why we should be careful about choosing the delay properly. Now, one way it is because we don't want to be totally correlated, we don't want to be totally uncorrelated. So we take the autocorrelation. What do you mean by autocorrelation? It is the correlation between the time series and a time shifted version of the same time series. So time shifted version is, if it is x of n here, it is of x of n plus tau. And you vary this tau. And for each value of tau, plot a graph of correlation versus tau. Somewhere if you take delay of up to this, you know that the correlation is very small. But if you take a very small value like 2 or something, the correlation is very high. So as in we do normally, when we don't know about the trend, we always go for 1 by e, things like that. And so we take it to be 1 by e, so here. So this is where the value falls to 1 by e. So we fix that as the proper delay time. So I am showing this for the temperature of Bangalore, how we get the delay time. This is how the delay correlation varies, autocorrelation varies, and you fix this. This is taken to be the delay, and it is in days now because it's climate data. Now there is another way of doing it. This is called calculating the mutual information. So mutual information definition is shown here. You calculate the mutual information again as a function of tau. So here again you take the time series and the time shifted time series, and the shift in time is now kept as a variable. And for each value of tau equal to 1, 2, 3, 4 like that, you go on doing it and then get the mutual information, plot it versus time. This is a schematic. And wherever it is, its first minimum comes, that value you take as the proper value for tau. So this is for a financial data. We find that the mutual information goes like this, and you take this value as the tau. And this is again for the temperature of Pondicherry. Mutual information. See, when you actually calculate for a given set, small fluctuations like this can happen. So what we normally do is you have to fit it with a curve and then look for a proper minimum. So we cannot take this as your minimum because these are small sort of fluctuations only. Fit it with a curve and then you see that this is the actual minimum in the data. Then take that to be your delay time. So these are the two. This one or this one?
The scales are different. So
Yeah. This is for financial data. This is very different. Number of this.
That side. But what is find as better? Right? To get the scale here.
Yeah, and here. So here it is that because, actually, no, here actually, because it is climate data, I put it in the actual measure as days. These are days.
Right.
Here, here, what happens is it is only number. I didn't put it in terms of any other because this is financial data. I didn't put it as days or years.
It's not the x-axis matters. It's the y-axis. So look at the scale there and look at the scale here. So
that's different.
I think approximately they might have the same level of.
Yeah. That's possible.
Yeah.
Good. Now coming to choosing the dimension. How do we know which is the proper dimension to fix it? So one method is the method of false nearest neighbors. So this I'll explain again. Again, there were some questions about this. So what I said is, suppose we have not chosen the correct dimension, but you are in a lower dimension, then all these points will be projected. It's like projecting from a high dimension to a lower dimension. So there will be large number of points which are coming together. And you calculate the distance between 2 points, let us say I and K, nearest neighbor K. For every point I, locate the nearest neighbor K, in, let us say, m-dimensional space. For example, if you start with m equal to 2, then calculate the distance between them as xi minus xk in two-dimensional space. Euclidean distance is okay. So that we call as a quantity Rm. Now you go to the next dimension, m plus 1. Again, calculate the same quantity between the same two points in the trajectory. So when you reconstruct, you get trajectory points in that higher dimensional space. So this will be a plot of xt versus xt plus tau now, because that is their next variable. So this is x at time t. The microphone. If you have taken only two dimensions, you have only two variables, xt and xt plus tau. But you have it repeatedly because you again go for the next time, find its t plus tau, again for every time. So you get a set of points. Like this. You take the distance between 2 points, let us say these 2 points, xi and xk, calculate the distance between them. Now you go to the third dimension. Suppose the actual trajectory requires a third dimension. That means when you go to the next dimension, these 2 points I and k need not keep the same distance, but because now you suppose they are resolved in the third variable now, third direction now. So the distance will increase. If it increases, we say this is actually a false neighbor. So for every dimension m, you calculate the total number of such false neighbors. For every point, you check the distance with its nearest neighbor. Like that, do for all of them. Then go to the next dimension. For the same pair, again calculate the distance and see whether it is increasing. And how do you say whether it is increasing? There should be a measure for it. That is given here. So you take the square of the distance at m plus 1 minus the square at m divided by this. So that's a normalized distance. Take its square root. And if it is greater than some quantity alpha, alpha can be very easily taken to be 1. If it is less than alpha, that means in the higher dimension also they are neighbors, which means they are actual neighbors. So then using this, you calculate the total number of false neighbors that we get. Plot this fraction of false neighbors versus the dimension, starting from 1, 2, 3 like that up to this one. Then you find that the number of false neighbors will decrease very fast for a deterministic system of finite dimensions. And then wherever it becomes 0, you say that is the actual dimension. Because after that, there are no false neighbors. Whoever are there as neighbors, there are actual neighbors. So the trajectory is properly and correctly resolved in that required dimension. You don't need one more dimension. But on the other hand, if you are doing for white noise, for example, it will not converge at all. The number of false neighbors will continue changing like that because there is no deterministic trajectory for white noise which tells you that higher dimensions are not required or they have a finite dimensional phase space. So this I am now showing for the temperature data for Bangalore. You see this is the percentage of false neighbors versus the embedding dimension, and then you find that at d equal to 5, this becomes 0. So when you are now, only one more thing you have to be careful when you are dealing with a large number of data sets and you are planning to compare them, we have to take the highest dimension that you get among them. So for example, in the climate data, some of them may give 3, some of them 4, some of them 5. Then we take 5 for all of them. So why are we justified in that? Because the measures that we are looking for, the quantities that we want to calculate, will saturate beyond its actual dimension. I will illustrate it with one case. So there are so many measures that you can calculate to check this. So one measure I will tell you is what is known as a correlation dimension. Those who have gone through this, we will know that this is one of the fractal dimensions of a system. Because the trajectory of such a nonlinear system in its actual phase space, the points on the trajectory are not uniformly distributed like a periodic system. So if you have a periodic trajectory, then you know that the trajectory points are always on a line for a given initial condition and it repeats. But when you have a chaotic trajectory, and if you look at those points, they are sort of randomly distributed over the whole attractor. I wouldn't say randomly, I would say non-uniformly distributed over the attractor, because of which there is they are actually something like a fractal. For a fractal, there are different dimensions you can calculate, and correlation dimension is one of them, which is the simplest to calculate for a time series. So what we now do is we first calculate a correlation sum, which says the probability that two randomly taken points are within a distance less than r. So that is calculated here. This Heaviside function tells you that if this is less than that, it is 1, otherwise 0. So like that. And then you calculate the average of that. This is called the correlation sum. And this certainly will depend upon your choice of R. If you are increasing R, you will get more and more points counted within that. So, but because there is a particular non-uniform distribution for a given trajectory, there is a scaling for this. This correlation sum will scale as R raised to D2, where R is the distance that you are using here. And therefore, this D2, which you can take by taking logarithms of this equation, is called the correlation sum. No, sorry, correlation dimension. So in general, for a given system, how you do is you take logarithm of R here, logarithm of C of R here, find the slope, that should give you D2. So this is one of the dimensions or measures that you can check to check whether the dimension is the correct one. So I'm just showing this, how this changes for a regular trajectory like this. See, for example, if this is your R, there are 2 points. When you increase R to double that value, you get 4 points. When you increase R, again 8 points. So if R is plotted here, the number is plotted here, it goes regularly like 2, 4, 8 like that. Because it's a periodic trajectory. Look at this trajectory. This is non-uniform distribution of points, which there are gaps here. So if when you increase this R from this to this to this, the number is not increasing like that. But there is a pattern in which it increases, and that is what is given by this dimension. So what you do is, to check the correct dimension, you have chosen the correct dimension or not, you can plot this D2 versus M, and wherever D2 starts saturating, that is your correct dimension to be used. Because as we said, all such measures that we calculate on the trajectory points will saturate after its correct dimension is reached. I'm just showing it for another case. How do you actually do it? You want to calculate the C of R, which is the C2 of R, which is the correlation sum against R. And because of noise and other effects, these parts we don't take, this also we don't take, these are called the size effect or edge effect. Somewhere in between there is a linear region, take the slope there. That gives you the D2 value for that particular M. And then this is for different M's. Then plot that D2 versus M, and if you take curve like that, you find it saturates, and then this error calculation is based on how you calculate the slope. So then we can say that if it is saturating at for a given M, that is correct. So this I am showing for a set of standard nonlinear systems. For a random system, random noise or totally stochastic data, they will not saturate. It will go on increasing as you increase M. But in all other cases, that will saturate. So that is again another test to check whether you have done the dimension correctly. So we said we can use FNN to calculate the dimension, and then calculate one measure, which is the D2 or the correlation dimension, which is very simple to calculate. And then all these are given in that TCN package also, how to do it with a lot of explanations, what are the things that you be careful about when you do it, etc. So you can check that also. Now I am just showing you some figures that I told you about the star data. These are RR-Lyrae family of irregular variable stars. These are the Kepler IDs for them, from which you download the data. And you see, look at the data, we don't see much difference between them. But these are the reconstructed attractors projected into 2D space. So you can see that the way that points are distributed on the trajectory in that two-dimensional space itself varies. And then you should be able to calculate some measures on this, which will tell you more about the underlying dynamics of each star. Yes. Yes.
These are different stars.
Yeah. These are different. The RR-Lyrae is a group or family of variable stars. We identify them with the Kepler ID because the data is from the Kepler satellite. And each one, the ID is shown here so that the data is from that star. That's all. I didn't put their names, etc. That's not very relevant. What's your question?
Essentially, the dimensions here corresponds to the major factors that affect the temperature data of the time series.
No, we are saying there is a correct dimension. How do you arrive at that dimension? So in this case, it is actually higher dimension. But I am showing you, just for showing it, I am doing a 2D projection. Higher dimension, in this case, if I remember correct, these are all dimension 4. Required dimension, some of them may be 3. Till, as I said, we want to compare large number of sets, we take the highest dimension among them. For each data, you have to calculate, find out what is the relevant m, and then you choose the highest one among them. Because for the taking a higher value doesn't matter, but lower value matters. You may run into errors. So this is just showing the two-dimensional projection so that we get to see how it happens. This is a set of binary stars. So binary stars can be classified into semi-detached, over-contact, and ellipsoidal based on, what are binary stars. One star goes around the other star. And there are variations that happen in the intensity. One big variation is eclipsing. One star may eclipse the other one. But other than that also, because of the non-linearity of its dynamics, other variations can happen. And then this is the data. You can look here, even looking at the data, we know that there is difference. But you reconstruct the dynamics. Again, I am showing only 2D projections, and then we can see that how the dynamics varies for them. And this is again another interesting example. These are ECG data sets. This is the healthy case, bundle branch block, cardiac myopathy, dysrhythmia, and myocardial infarction. I don't know, you are too young to hear about such diseases, but these are diseases of the heart. And the ECG data from the heart varies based on this. And these are the variations that you see. So if you recreate the dynamics, can we make out some differences? This is for the healthy one shown in green. These are all different diseases which I showed earlier. So you can see that the structure of the dynamics that is coming from that. See, in this case, you can think of human heart as a spatio-temporal system. And there may be large number of variables required. As you asked, we may not be reaching the correct variables, because just by saying that it is 5-dimensional, we are projecting in 5 dimensions doesn't mean that, or 3 dimensions doesn't mean that you can have an equation like x dot, y dot, z dot, because it's an average response. But just to get a structure that is involved in the data, we are creating a dynamics. In regular cases like standard systems, it will be exactly the same. But in the case of heart and all, we don't know whether we are getting, and you can, because you get a structure, but there are some work in the case of heart at least, where people have synthetic heart, which means you can actually write some equations and model that, and then from that you can actually reproduce this data. So the advantage there is, for every disease, they know which parameter to tweak so that you get exactly the data for that particular disease like this. And then people can work on that. But here, what I am showing is just the recreated dynamics, and to drive you the concept that the attractor itself is changing, the distribution of points are changing. Therefore, the measures that you get from them also should change, and that should give you some indication about the particular disease and things like that. So that is, once the dynamics is now recreated, our point is to go for the recurrence plot analysis. This also we said the other day. We know that recurrence can happen in all these cases, because you see these are all bounded trajectories. So given after a certain interval of time, every point here, another point will come close to that. None of these will repeat exactly, but they will come very close to that. So if you have a close neighborhood of, we say epsilon neighborhood, the data is repeating, the point on the trajectory is repeating, then you call it a recurrence point. So to count how such recurrence points occur, we take again the distance between 2 points xi and xj, and if it is less than epsilon, we say this recurrence matrix Rij will have a value equal to 1. Otherwise, it will have a value equal to 0. So basically, you get a matrix of zeros and ones, and from that, you can actually plot it also. Yesterday, in the previous lecture, I didn't show you that, but this is that PyUnicorn package I talked about. This also will give you all these details. Now here, another crucial thing is the choice of that epsilon, because how many points you get on the recurrence matrix, once we get on the recurrence matrix, depends very crucially on this epsilon. You have to be sure that you are using the correct epsilon. So there are several methods. So some people say that just take it to be 10% of the maximum distance in the reconstructed phase space. Because this again is to compare data sets. You want to be the same for all of them, that's why you do it. Another way is to calculate the recurrence rate, which means the number of points that recur divided by the total number of points. That is calculated like this. So they say that, okay, for whatever is the different types of data, if you fix your RR, recurrence rate, to fix that recurrence rate as some value, let us say 0.2, which should be the epsilon value for that data. For the next data also, you want RR to be 0.2. It may give you a slightly different epsilon, but that's okay. Something you are fixing. Just like you fixed your dimension, You fix your RR and do it. What we nowadays do is we plot this distribution. This is actually embedding vectors, the distances, pairwise distances calculated on the embedding space. So you have a 5-dimensional space. You can calculate the distance between every pair of points in that 5-dimensional space, take its distribution. The distribution may go like this, and then you fix it as the 8th percentile or the 5th percentile as your epsilon. This is also one way of doing it so that we have some idea how to fix it based on the distance distributions that happens. Because you don't want to take epsilon to be very large, then what happens is all of the points will be shown as recurring. That is not correct. So once you do all these things, you see for a periodic system, they recur after a same interval of time because it's a periodic trajectory. So the recurrence plot will have all diagonal lines because these are the points, both are points actually. Along x-axis is I values of the points on the trajectory, y-axis also the same. So at every definite interval of time, they are repeating, so you have only diagonal lines. But in a nonlinear system, like Lorentz system or something, this is a Lorentz system if I remember, this one is anyway there. The major diagonal will be there because that is for I equal to j. But for everywhere else it need not. But because there is some structure in the dynamics, there will be some diagonal lines like this and then some points like that. But if it is pure noise or stochasticity, there are no diagonal structures at all. There are all some sort of randomly scattered points. This is actually a data from a stock index values. You see there is some structure there. So this structure is also something which we can capture using definite measures like determinism, laminarity, etc. Because we are dealing with networks only in this program, I am not going into that. But this pattern will tell you something more. But this plot gives you some idea about the information about time also. How these points are changing over time. While when you make it into a recurrence network, we have only geometric characterization. The dynamics is lost. Dynamic information is lost there. So therefore, many people do the recurrence plot also. So I will show you the recurrence plot for our climate data. This is actually the data from Manali at 2 different periods for temperature. These trajectories we saw the other day. You see how different this recurrence plot also look like. So if you do the full thing also, you know that somewhere in this time there is one type of pattern. Again, it changes in time. That's why I said time information is also there in the recurrence plot. So this, at least, but looking at these two, we know that there are changes. Even though it is not that evident from the trajectory, that is very clearly evident from the recurrence plot. And this I showed you the other day, Pondicherry at 2 different times, Ladakh at 2 different times. So this is one reason why we want to look for the changes in the dynamics of these locations using the temperature data or the humidity data. Now coming to construction of networks, this also we showed that day. These are the points on the trajectory that we have. Then we calculate the distance between 2 points I and j as dij. Every pair of points we will do it. But one pair of points I and j, if you calculate this distance, this m is again the dimension. Capital M I used earlier, now I forgot, this is small m. So dij is less than some epsilon, then you say we will put a link between them. So here for y2, the second point here, within that epsilon you find y9, y1 and y5 are repeating within that. So we connect all of them. So go on doing that, and then what you get is an adjacency matrix. If dij is less than or equal to epsilon, we say the matrix has value 1, otherwise 0, and we don't want any self connections or self loops, so AIE, diagonal elements are all put equal to 0. And then we get this adjacency. This is, if suppose this is the network, this is the shape, this is the type of adjacency matrix that you get. And as we said earlier, this adjacency matrix can be obtained from the recurrence matrix also by removing the diagonal elements. So Rij minus delta ij is your Aij. But once you get the adjacency matrix, it contains all the information that is required from the network in that. Whatever you want to calculate, you can calculate. But again, the choice of epsilon is very crucial here, because what you want is, you want all the points on the trajectory to form a single network. So in the context of network, you say it's the percolation threshold. If you don't have it, if you have a slower value, then you won't get it, they will not be connected. So you go on increasing until you find that all of them are connected. But if you go for higher values, it becomes randomly connected, which we don't want. So basically, you have to fix a lower bound for epsilon and an upper bound for epsilon. So how do you fix the lower bound? The resulting recurrence network has to remain as one single cluster. That is how you fix your lower bound. And upper bound is, all the network measures should give you some meaningful information, which means If you had taken a large epsilon, they tend to become random networks. We have actually shown that by increasing epsilon, it will go from the recurrence network to a purely random network. So that we don't want. So we have to fix it. So how do you do it? So to fix the lower bound, there is a connectivity measure that comes from graph theory, where you, from the adjacency matrix, you take the Laplacian matrix. That is obtained as the diagonal matrix of degrees minus the adjacency matrix. So if the ith node has degree equal to 3, the diagonal element of that diagonal D matrix will be 3. So this is a diagonal matrix. For every node, it gives the degree of that. You are subtracting the adjacency matrix from it. So what happens is, the adjacency matrix has one wherever there is a connection between I and j. So now you are subtracting that. So you will, and the degree will come as the diagonal element. So when all these are subtracted, you will find that the row sum is equal to 0 for the Laplacian matrix. You can just think about it. And then, therefore, the smallest eigenvalue of the Laplacian is always 0. But we want to look at the second smallest eigenvalue, that is a connectivity measure for a network. So what you do is you go on increasing epsilon, calculate the second smallest eigenvalue, and the point where it separates from 0. That we say is the lower threshold, lower cutoff value for this. We said we want an upper bound and a lower bound. Lower bound can be obtained from this. This is very simple to do. Now, how about the upper bound? So what we have done is, we want to see that the measures that we calculate from the recurrence network should be different from the measures of a totally random network. So then only it is meaningful. So what we do is, we calculate one of the measure, which is the characteristic path length, which we defined the other day, against this epsilon. Then you find that this is the lower threshold, because before that the network is not fully connected. That is why CPL has this type of behavior. But after that, as you increase epsilon, we find that the CPL goes on decreasing, and at some stage we cannot differentiate its value from that of a random one. This is from the noisy data, this last one. This is one for Lorentz and the other for Rosler data. So we will fix it somewhere here such that the value for CPL that you get is very different, significantly different from that for a stochastic data. So that is how we fix the upper cutoff. So between this, anywhere you can take it. And we also find that it depends on the embedding dimension. When you go to higher and higher dimension, obviously you have to take more and more larger and larger values for epsilon. For every dimension like this, we have calculated based on the earlier graph, this type of calculation. We have calculated what should be the lower cutoff and the upper cutoff. So within that, somewhere you can actually fix your epsilon and then get the recurrence network. Normally, if you are doing both recurrence plot analysis and recurrence network analysis, you fix it for recurrence plot, use the same epsilon for recurrence network also. That's also one convenient way of doing things, that's all. Now, here also, depending upon the dimension, so how do you fix the dimension also, we can check, because the dimension has one beautiful property that some measure will saturate. Beyond that, it won't change. So in the context of trajectory, we said you can do correlation dimension and check it. But in the context of network also, you can check it. So I'm showing it for a 4-dimensional chaotic, hyperchaotic system like the Shen system. We are calculating, constructing the network and taking its degree distribution. You see, as you increase the dimension, the degree distribution shifts. And when it reaches the actual dimension 4, the 5 also is on top of it. So the distributions are actually not changing beyond that proper M. So if you have got the proper M, you know for sure that that is the proper M, because increase in M will not change the degree distribution further, because the informations that you get from the network very much depend on the degree distribution. The other measures that we take, degree we already defined, link density we defined, and CPL also we defined, and clustering coefficient is another measure which also we did not define much, but that is shown here. That if you consider the links of a node like this, we can define a local clustering coefficient like this as the actual number of links divided by the possible, actual number of closed triangles divided by the possible closed triangles. So here there are 3 possible closed triangles, but only these 3 links it has. So only one triangle is closing. So that ratio is the local clustering coefficient, and averaged over the network gives you the total clustering coefficient. Now I am showing you some beautiful pictures of data from black holes. These are 2 states of GRS 1915, which is a black hole, X-ray data from a black hole. and you are reconstructing the dynamics. You see, based on the data, the reconstructed dynamics, network has a different structure, which you can actually calculate in terms of measures. These are the same RR Leray stars I showed you in the beginning, the data I showed you, and the attractor also I showed you. When you reconstruct the recurrence network from it, you see their structure is very different. Therefore, all the measures will be different, so you should be able to differentiate them. And these are for the binary stars, 3 classes of binary stars which we showed. Here also the network has very different structure, and then we should be able to identify them from the calculated measures. Multifractals, what is it? Multifractals of?
PF, multifractal retrended fluctuation. Because that will give you some.
Yeah, that's right. That I have not done.
Right.
Yeah. Now, calculating these measures, as I said, has one use is for classifying them. So we now use a clustering algorithm, and then we use these 2 measures, the clustering coefficient and the characteristic path length. And then we see whether these points, all these over contact is shown in one color, semi-detached is another color. So in this space itself, we can see. So now if we have data from a binary star whose classification is not known, we can calculate it and see whether it falls into this region or in this region, and then you can identify them to which group it belongs. So this is very important in astrophysics because we deal with very large number of stars and observations and data. So we should be able to classify them. That's one thing. And this is the recurrence network from the ECG data. This is for the healthy person. This is bundle branch block, cardiomyopathy, dysrhythmia, myocardial infarction. You see how different they are. So we should be able to say something about the measures from them. And then we should be able to say whether that particular person is having any of these diseases or is he totally normal. That should be possible. But this is only half of the story because this is ECG is normally taken from 12 channels. At least 6 channels are important. This is the closest to the heart, which is the second channel. Data of that only. I will later show you what happens in the other cases. Now, another thing that we said in the previous lecture is how does this help us to identify some transitions that can happen in the dynamics over time. In the context of climate data, we have shown it from 1948 to 2022. And we said that around 1975, 76, some change we observed, and beyond 95, some significant change we observed in most of the locations. Similarly, this is another situation I'm just showing you. This is the financial data, stock market indices over time, 1998 to 2022. So even by looking at it, you can see this time around 2008, that is the global financial crisis, GFC. And this is, what is this? Around 2020, what happened? COVID. So that also affected the financial market drastically. So we can easily see, looking at the data, so we were tempted to do some analysis because it's so evident from this that something has happened to the dynamics underlying the market. That is why the data has gone to this many changes, etc. So these are the networks, and I'm showing only, we have analyzed actually 26 of them, but we are showing only a few. These are the networks generated from the financial data of these 4. One USA, one France, one India, one Japan, like that. Market, and then the degrees, higher degrees are shown in red color and lower degrees in blue color, like that, so that we will understand what happens. Now here, this is the CPL measure versus time. We are showing in pairs, USA, one market in USA, UK, India, Hong Kong, and then Japan, China, France, and Italy. So you see, before 2008 itself, you can see that there are some changes happening in these measures. So CPL value goes on increasing, which, as we said in the previous day, increasing trend means, in CPL means, there is some stochasticity coming into the system. It becomes more irregular. Anyway, in the beginning itself is irregular because all these data that I showed you, we have proved them to be nonlinear in nature. So they are not chaotic and they are not regular trajectories. However, the irregularity increases. And that we can actually see that trend starting earlier also, before even it reached the final crisis. We can actually see that. That's what is happening. And immediately after that crisis, it is coming down also. This we can see in most of these markets. In a way, we can see which was the first market that may crash. This is a billion dollar problem, so I don't want to make any comments on that. But it is very clear that. And how do we explain that? Because there were some trends which indicated that something is going to happen, just like the presidential election people anticipated, no, something will happen to financial markets. Like that, people can say something, and because of which people started buying and selling these things, shares very randomly, just like that. So that introduces some stochasticity into the dynamics, because of which we find CPL increases, and as we showed in the previous day, the link density will decrease also. So that means we can clearly identify what happens during that time, etc. Now this is again, once again I am showing you what happens for the temperature data of different places. So here we were interested in how many locations go together in their changes in dynamics, not the actual values, but over time, how do they change? So how many of them became more stochastic or more irregular, how many remained after that, like that. And we found that we can classify them based on the variations in CPL and LD into 5 clusters. So this we have shown earlier, so I am just showing you again, just to understand the significance of that. And this is from the relative humidity data. Here also you find that Tawang is showing some behavior which is very different from all the others, but others we can group. For example, these 3 again going very together. These are all coastal regions except Bangalore, but they are also showing very similar behavior. The rise and fall may happen almost at the same time. That is how you identify that. And then we can say that. And this we have again shown as a cluster plot, scatter plot, where the changes that happen, whether it is decreasing, this is red color, increasing is in blue color. So between the CPL and LD, they have the opposite effects. So we can actually see what happens. This also I have shown earlier. So these are the informations that we got from that, and we could actually relate it to some of the known or established changes in climate, which has happened over time. So let me skip all these things. This is for relative humidity. Now, there are some issues. That also was a question in the previous lecture. How do we do some sort of a null hypothesis and verify that whatever you are getting is correct? So normally what we do is we do a surrogate data analysis. The surrogates are generated from the data itself. So one simple way of doing it is just shuffle them. So there is a sequence in which these observations or data or value points come. So that is very important because that is how it is happening. So that tells you everything about its dynamics. So, but if you shuffle them randomly, then all that information is lost and it will be just like a random set of points. So we start with the null hypothesis that the data is from a linear stochastic process, which means it is totally random. Then you test it by computing a measure like our D2. That is one way of doing it. It can be any measure that we calculate from the recurrence plot or the recurrence network. And do it for all the surrogates also. The surrogates can be generated for recurrence. There is a method called the twin surrogates by shuffling the points on the recurrence plot itself. But from the data, there is amplitude adjusted Fourier transform. So you take the Fourier transform, shuffle its face in the Fourier transform space, then take the inverse transform. That's the method. So these also methods are given in this Tissian package, how we do it. So then at least 10 surrogates like that you make. Then calculate this measure using all the 10 of them and compare it with the value that you got for the actual data. So then you can find the effect of colored noise, especially colored noise is otherwise very difficult to distinguish between the data and white, unlike white noise. So we can check whether the data comes from a deterministic system or from a pure noisy data. So we can actually quantify that, the difference between the value for the data and the average value of all the surrogates together. We can distinguish for any measure. I am showing it for D2 here as a normalized mean sigma deviation. That is what is shown. So this is the schematic of the total surrogate analysis. You start with a null hypothesis, this is the original time series, generate a number of surrogates from the original time series. That gives you the surrogate time series. Calculate any measure with all these, with the data also, that particular measure, whichever you are using. Then check it, how they are different or not, compare them. If it is the same, accept it as a null hypothesis, the null hypothesis is correct. If not, reject the null hypothesis. So this is the basic schematic behind the surrogate data analysis. This I am showing here for D2 versus M for data. You see for Rosler data, Lorentz data, these are surrogates. They behave very differently compared to the data. But on the other hand, when you have colored noise, it's very difficult to distinguish it from the data. So that is how you can distinguish them. I have 5 more minutes, no? Just to show you, I'm not going into details, there are some recent trends instead of just constructing a recurrence network, you can construct a weighted recurrence network. So weights can be added to each link. Now in the earlier, we are just putting a link. We are not worried about all links have the same weight or something like that, and they are all undirected links because the adjacency matrix is symmetric. So whether I is connected to J or J, assume that J is connected to I, it's the same thing. But sometimes people do a slightly deviated approach where they say that some time information can be incorporated into the recurrence network by giving the direction in time. So if I occurs first in time, when you connect I and J, you put an arrow from I to J only. You don't put an arrow from J to I. That is one new approach people do. So that, as I said, otherwise, recurrence network has only geometric information. Dynamical information is lost. But that can be brought back into recurrence network also by putting these arrow directions. That is one thing. The second thing is, you say that if the distance between I and J is within epsilon, you put a link. But within epsilon itself, that distance can be very different for a set of points. So suppose the distance difference is, suppose your epsilon is 0.5, there can be distances which is 0.1, 0.2, 0.35, 0.45, like that. So when you put only a link, you are taking all of them to be the same. So some, in what is it called, one more level of information is lost there. So you can add it by putting a weight to the link depending on the actual distance. The smallest will get the smallest weight, or, I mean, normally it's the other way. The smallest will get the highest weight, and then go on putting a weight to the link based on the actual distance within that epsilon. So that is one way of constructing the weighted network. Here we are doing it differently because we want to put a weight factor by looking at their degrees. So I and J, each one will have some degree because they are connected to other nodes also. So we will assume a weight like root of ki kj by the maximum degree k max, so that for the maximum node having the maximum degree, it will be equal to 1, otherwise it will be less than 1. Then instead of degree distribution, in a weighted network, we will calculate the strength of a node as the total weight, and that is the degree distribution, and link density will be weighted link density, and then we can calculate the link strength distribution. Here I am showing it for white noise and for Lorentz. You can see that their behavior is very different. This is totally exponentially decaying, but here there is a scale factor also. So this gamma here can be characteristic of the underlying dynamics, which can be another measure. Now I come to a situation where you have to analyze a large number of data sets together and compare them. So I have compared in the case of climate data by looking at the transitions that happen in the dynamics. Suppose that is not our interest. In general, we want to see how they differ in like this case. So this is actually ECG data from two different leads, lead 2 and lead 4 for two typical data sets. This is the healthy one, and this is actually a case of bundle branch block. You see, in this case, as obvious from the name of bundle branch block, one lead is giving a totally different structure here. So because of which the calculated measures from that also will vary. So you can, how do we finally compare them? So each one, we construct a network out of each data, and then we look at some measures within them so that we can compare them. That's what we do. So this is what we do. One data set, another data set. One data set is, this is the recurrence network from this data, this is from the other. And then we say this is a multiplex recurrence network because we are connecting every I here, ith node here to the ith node here. So in between connections are all I to I. Then you call it a multiplex. If you give another set of connections, it is multi-layer. Here we are considering only multiplex like this. And then there are some measures which you can compare and contrast between these layers. Then it should give you some information. So this is what we do. We take only the 6 channels of ECG, generate this. So here in the adjacency matrix, every element is a matrix because that is one layer itself, one network layer like that. And these are the different layers schematically shown here. And we'll just go through this because this is so many types of this. We can check how much edge overlap is there between this layer and this layer. Then we take the degree distribution of both of them and look for the similarity underlying the degree distribution. One is mutual information, the other is cosine similarity. Then you can calculate any measure like clustering coefficient and take its distribution and then compare them. So this is one way of comparing the differences and similarity between different data sets. So I am in time, let me summarize. So we argued and established that there is a dynamics underlying every data, and this dynamics is recurring in time. So this recurrence pattern in the reconstructed phase space will give you some information about the underlying dynamics. So this pattern is to be captured through some measures. And here we are mostly showing that for recurrence network, and we have shown some applications. So the recurrence measures also can indicate transitions in the dynamics, and we can have multivariate data by constructing multiplex networks, we can analyze them. And in the context of climate network, these are my earlier conclusions, which we have already seen, how we classify them into clusters and relate them to some epochs or shifts that is already reported in for climate. Let me stop here. Thank you very much.
Samir.
Yeah.
How the direction is determined whether the nodes are.
So in time we know. See, you have a trajectory. The data is coming as a sequence in time. So there is time information in your data, no? So if you are taking from 1948 to 2022, we know 1948 onwards, there is a time index in days or whatever units. So that time information is there. For some cases where that information is not required, we just call them 1, 2, 3 like that, up to 30,000, 50,000 like that. But if you want to keep the time information, the way in which they occur, that itself is in time. So if you are taking the ith node here, jth node here, we know that jth value of that node comes after this I. So this is time information. So if you want to make a directed recurrence network, you will put an arrow from I to j only, not from j to I. So what happens is the adjacency matrix is no longer symmetric. So some of the properties like Laplacian we showed, those will not stand, but other measures you can calculate with that time information.
Surrogates, this is not possible.
Those surrogates are meant to see whether that is purely random or there is a time information. So you compare that surrogates related measures with the actual measures from the actual data. If there is a large difference, that means data has some time information, it is coming from a deterministic dynamical system. If this is either contaminated with too much of data, even then I add noise to the actual data also, it will be equivalent to surrogate. So surrogate analysis is just to check whether there is a difference and this is actually like that. Okay.
The application side, can these structures be into a learning machine and
Yes,
whether
can be done. We have a paper on that, I didn't show that reference. What we do is we calculate the recurrence measures from a large number of data sets, periodic, chaotic, hyperchaotic, random, like that. And then we have a machine learning algorithm where you train that with half the data, then test with the remaining half. I can send you the reference if you want. There, but normally people do it with statistical measures. What we have done is we have used the recurrence measures itself, recurrence network measures and recurrence plot measures. And then we have applied it to star data also and showed that it is able to classify properly. Like that. Yeah. Now we are further working on it to make the image processing from the recurrence plot itself. Rather than computing the measures, it will save time. So that we are actually doing. We will see. We'll put it up as a software package somewhere. Okay. Thank you.
So you have time series data from multiple discrete points in different scenarios, right? And you're doing a lot
multiple discrete points means we will say,
like for example, climate system.
So one location, for example, Bangalore. We have the temperature data of Bangalore.
Right.
This is actually, we don't have a continuous data, but this is with some time gap. So we bend it to 2 points per day. Actually, the data is from NSEP, where they have it 6 hourly. So we bend it so that we have 2 points per day, something like that. And then those are considered as discrete points then. Yeah.
Right. And so suppose you had so in climate-like system, you don't have the parent model or the full thing,
of
right?
Course.
But in some cases, you could have a parent model, a set of nonlinear PDEs. And you could generate data from the whole thing and look at a subset of this. And now how much of this would converge to the full thing? Have you done?
Standard systems, we have shown it. I don't have a figure for it. Lorentz system.
Right. So those are
you take the Lorentz system.
Low dimensional. Right?
Low dimensional. Let us say Shen system is 4 dimensional. So you take the Lorentz system, take only its X variable data, reconstruct the dynamics using this. The topology is exactly the same. But if you look at the value at a given time t equal to 10 seconds on the actual values and the same time on this, it may not match. But the statistical measures on the distribution of points on this attractor, reconstructed one and that one is the same.
Right. So let's say Lorentz is derived from a Rayleigh-Bénard convection kind of system, right? So now I don't think we can gain much info about the relay Maynard system by looking at Lawrence.
That we cannot.
Right. So that's the kind of question I'm asking. How many points do you need? How do we talk about the parent system? Because
You are
ideally, that's
thinking
what you
about
want
a
to do.
spatial temporal system where you have partial differential equations.
That's an example. So
That's
for
an
example,
example.
the big problems you're looking at climate and all, right? You need to say something about the big system, right? So
That's
having
right.
local data.
Yeah.
How much of the big system are we learning?
No,
by
but
looking at
what
the-
we can do is we look at each point, spatial point, take the data, and then you do some connectivity analysis like the multi-channel ECG. That is one way of doing it. Or consider each one as separate. Then take a correlation of the calculated measures. Rather than taking correlation of the time series, you construct the dynamics and then look at the correlation among the measures. Then you can see whether they all are agreeing or not. And you can make it more and more accurate by taking more and more spatial points. That's all we can do now. Yeah. Okay.